Hello, my name is João Almeida. I am your lecturer for this video in which I will talk about seismic hazard. I will first start by recalling how earthquakes usually occur and their waves propagate. I will then define seismic hazard and discuss how we can measure the size of an earthquake, namely in terms of magnitude and intensity. There are different types of earthquakes. They can be due to volcanic activity, collapse of underground cavities, or even produced by blasts or explosions. However, the major source of large earthquakes is definitely the rupture of the Earth's crust, namely in the so-called interplate earthquakes. The next few slides will bring back to memory what you most probably learned in primary school. The Earth is divided in four major layers: the inner and outer core, the mantle, and the crust. The skin, or the hard outer layer of our planet, is called the lithosphere, and it is made up of the crust and the cool, dense, and rigid upper part of the mantle. However, our planet's skin is not all in one piece. It is composed of many pieces covering the surface of the Earth, called tectonic plates. These tectonic plates are not immobile. In fact, the difference in temperature between the core and the crust creates convection currents that force these plates to keep slowly moving around in different directions at different speeds, sliding past one another and bumping into each other. The edges of these plates are called plate boundaries. The boundaries are made up of many faults, and most of the largest earthquakes around the world occur on these faults. Since the edges of the plates are rough, they get stuck while the rest of the plate keeps moving. When the plate has moved far enough, a rupture stress is reached at a point. The two mass blocks on either side of the fault unstick and slide along the surface of the fault with an instantaneous release of elastic strain energy. The point within the Earth where an earthquake rupture starts is called hypocenter or focus. If its depth is up to 60 kilometers, we say that it is a superficial earthquake, while deep ones have hypocenters between 300 to 700 kilometers. The epicenter is the point directly above the hypocenter at the surface of the Earth. The energy released in an earthquake is transmitted in the form of seismic waves, such as the faster compressional waves P and the slower transverse waves S, which propagate inside the Earth in a radial direction, undergoing phenomena of reflection and refraction. Until now, I recalled how earthquakes originate and their waves propagate. Seismic hazard refers to all the physical phenomena caused by earthquakes that may be potentially damaging, either directly for human life, for physical assets, or in any other social, economic, or even environmental dimension. They include ground shaking, which can make it difficult for us to stay on our feet, or more importantly, make structures collapse, but also surface rupture, for those cases where the fault does not remain buried or hidden under the uppermost layers of rock in the crust, tsunamis, and you may recall that in the Indian Ocean in 2004, as shown in this picture, or after the recent Japanese earthquake of 2011, liquefaction, when a water-saturated soil temporarily loses its strength and behaves as a fluid, or even landslides and rockfalls. Instruments that characterize the ground motion have been developed since ancient times, as Zhang's seismoscope, where a bronze ball drops from one of the 8 dragon heads to the toad's mouth to indicate the earthquake direction. In more classical seismographs, as represented in this sketch, when an earthquake causes the ground to shake, the base of the device shakes too, but the hanging weight does not. The relative displacement between the shaking part of the seismograph and the motionless part is what is recorded. Modern seismometers, based on analog and digital technologies, allow not only to register the displacements associated to ground shaking, but also ground motion records of acceleration and velocity. Besides, these records can be measured along any two perpendicular horizontal directions or even along the vertical axis. Using the existing networks of seismometers, scientists can then determine exactly where the earthquake was, based on the speed difference between the P and S waves and by using a method called triangulation. When it comes to measuring the size of an earthquake, there are basically two measures that can be employed: magnitude and intensity. Magnitude quantifies the global energy released by an earthquake, while intensity expresses the local earthquake effect, this is, at a specific site. It is therefore easy to understand that, for each earthquake, there is only one magnitude value. Instead, many parameters can be used to measure the intensity. With respect to magnitude, there are several scales. Although the Richter scale developed in the 1930s is perhaps the most famous, the one which is commonly used for official purposes is the moment magnitude, developed in the 1970s. It is based on the seismic moment of the earthquake, which is proportional to the average displacement along the fault and the size of the area that slipped. Just to give you a rough estimate of the amount of released energy, consider that a magnitude for earthquake is approximately similar to the explosion of a small atomic bomb within a radius of 100 kilometers. An increase of one step on this logarithmic scale corresponds to approximately 32 times increase in terms of the amount of energy, which means that, for instance, a magnitude 7 earthquake is around 100 times bigger than a magnitude 5 earthquake. This should put things in perspective if I tell you that a few earthquakes with magnitude larger than 9 have been measured over the past 70 years. The maximum magnitude registered until today was approximately of 9.5 in Chile in 1960. Seismic hazard is, however, typically expressed through the intensity of ground shaking from an earthquake at a given site, which can be measured using a number of parameters as stated before. These can be categorized into two types: intensity that is assigned based on observations, also known as macroseismic intensity, and intensity that is measured from instruments such as accelerographs, commonly known as ground motion parameters. The conversion between observational and instrumental intensity involves much uncertainty. Let's see why by looking in more detail into each of these categories. Following the definition of Bolt, observational intensity is a measure of ground shaking obtained from damage done to structures built by humans, changes in the Earth's surface, and felt reports. It is an indirect measure for the ground shaking, being particularly useful for historical earthquakes. This is where no records of the ground motions are available, or for recent earthquakes in regions where no accelerometers were installed. The most famous scale is probably the modified Mercalli intensity, MMI. However, there are others. For example, this table presents the short form of the European macroseismic scale EMS 98, which is a 12-point scale. Roman numerals are used to emphasize the fact that these scales are neither continuous nor linear. The level 3 corresponds to the level of human perceivability, while damage in structures initiate in level 7. The top 2 degrees are rarely attained, if ever. This figure on the right shows the application of a macroseismic intensity scale to the Chile earthquake of 2010. Note that, due to local site effects, the maximum intensity does not necessarily occur at the epicenter. Further, one can also observe the isointensity lines, which bound in an approximate manner a region with one predominant intensity. For what concerns ground shaking as recorded by seismic instruments, a large number of parameters can be considered. One can, for instance, take the maximum absolute value of the ground acceleration during an entire earthquake record, the so-called peak ground acceleration or PGA, or any other ground motion parameter, such as the peak ground velocity or the area's intensity, which measures the energy within the record. Seismic hazard, however, is not only characterized by location and intensity. Its frequency or probability of occurrence is also required. This can be expressed by the return period T of an earthquake, which is the mean time between the occurrence of two earthquakes with a magnitude equal or larger than the specified value. Finally, seismic hazard can be expressed in the form of hazard maps, which show the levels of ground motion with a given probability of exceedance over a period of time. This example, for instance, displays the peak ground acceleration for a 10% exceedance probability in 50 years, as obtained for Europe by the program SHARE. In a nutshell, in this video we have seen how earthquakes generate and their waves propagate, how we can record them, and how we can measure their size, namely in terms of magnitude and intensity. Many different intensity measures can be used to express seismic hazard due to ground shaking at a given site or region. Besides, seismic hazard due to natural earthquakes can be characterized probabilistically, and it is approximately constant in time. In other words, the seismic hazard here in Lausanne, where I live, is expected to be approximately the same today or in 100 years' time. Does this mean that the seismic risk of this region or any other region will also be the same in 100 years? The answer is no, and the reason is that seismic hazard is only one of the components that influence seismic risk. I will explain this in more detail in the video of week 2. See you there.